Welcome to Calculus 1. In this lesson, we will introduce one of the most important ideas in calculus, the concept of a limit. Limits allow us to describe what happens to a function as the input approaches a particular value. As we will see, the value of the function at that exact point may not even exist. What matters is the behavior of the function near the point. We will learn how to estimate limits using tables and graphs, examine several situations in which limits fail to exist, and distinguish between the limit of a function and its actual value at a point. Let's get started. We have three primary goals for this lesson. First, we will learn how to estimate a limit from a table of values and from a graph. Second, we will examine three common ways in which a limit can fail to exist. And finally, we will learn to distinguish between the limit of a function and the function's actual value at that point. The central idea to remember throughout this lesson is that a limit describes where a function is headed, not necessarily where it ultimately arrives. Let's begin with an example that illustrates exactly why we need limits. Consider the function f of x is equal to x squared plus x minus 6 divided by x minus 2. Notice what happens when we substitute 2 for x. Both the numerator and denominator become 0. Because the denominator is 0, the original function is undefined at that point. However, the numerator can be factored. Once we factor it, the common factor cancels, as long as the input is not equal to 2. Therefore, everywhere except at 2, the function behaves exactly like the line shown on the graph. The graph is simply a straight line with one missing point. That missing point is represented by the open circle at the coordinate 2, 5. Now consider what happens as the input moves closer and closer to 2. Approaching from the left, the function values move towards 5. Approaching from the right, they also move toward 5. Because the function approaches 5 from both directions, we say that the limit, as x approaches 2, is 5. Notice that we are not asking what the function equals at 2. The function is not defined there. Instead, we are asking what value the function approaches as x gets closer to 2. That is why the limit is about the trip and not the destination. We can also see this behavior numerically by constructing a table. On the left side of the table, the x values approach 2 from below. When x is 1.9, the function value is 4.9. As x moves closer to 2, the outputs move closer to 5. We see 4.99 and then 4.999. On the right side, the x values approach 2 from above. The corresponding outputs are 5.1, 5.01, and 5.001. As the inputs move closer to 2 from the right, the outputs move closer to 5. The function remains undefined at exactly 2, which is why we have a question mark in the center of the table. But that missing value does not prevent us from identifying the number the outputs are approaching. From both directions, the function closes in on 5. Therefore, we estimate that the limit is 5. However, a table only shows us finitely many selected points. A function could behave unexpectedly between those points. Therefore, a numerical table can strongly suggest a limit, but it does not prove that the limit is correct. Numerical and graphical methods help us estimate. Later, algebraic methods will also allow us to confirm exact limits. These three graphs illustrate an essential fact about limits. In the first graph, the function is undefined at 2. We see an open circle and no solid point. In the second graph, the function is defined at 2, but its value is different from the number the surrounding graph approaches. The open circle is at a height of 5, while the solid point appears somewhere else. In the third graph, the function is defined at 2 and its value agrees with the limit. Despite these differences, all three functions have exactly the same limit as x approaches 2. In every case, the surrounding function approaches 5. A limit examines x values near the point, not the value at the point itself. Consequently, the function may be undefined there, defined at a different value, or defined at exactly the limiting value. None of these possibilities changes the limit. The distinction between the function's value and its limit is extremely important. Now it's your turn. Use the graph of p to answer the 4 questions shown on the slide. The first question asks for the limit as x approaches 1. The second asks for the actual function value at 1. The third asks for the limit as x approaches 4. The fourth asks for the actual function at 4. Remember that 2 of these questions ask where the graph is headed, while the other 2 ask where the function actually is. Those are different questions. Pause the video now, write down your 4 answers, and then continue when you are ready. Let's check your answers. As x approaches 1 from either direction, the graph approaches the open circle at a height of 2. Therefore, the limit as x approaches 1 is 2. However, the actual function value at 1 is determined by the solid dot. The solid dot is at a height of 4, so p of 1 is 4. The solid dot does not affect the limit because the limit is determined by the surrounding behavior. Next, as x approaches 4, the graph approaches a height of 5. Therefore, the limit is 5. At x equal to 4, there is no whole or separate point. The point on the solid line, the point on the line is solid, so the actual function value is also 5. In this case, the function value and the limit agree. The main lesson is that a limit is decided by the approach, not by the dot. For a finite two-sided limit to exist, the function must approach one real number from both sides. There are 3 common ways this can fail. First, the 2 sides may disagree. The function may approach one number from the left and the different number from the right. Second, the function may become unbounded. Its values may grow beyond every finite bound instead of settling near a single real number. And third, the function may oscillate. Its values may continue sweeping between different levels no matter how close x gets to the point. In every case, we ask the same basic question: does the function settle near one number? If the function does not settle near one real number from both sides, then the finite two-sided limit does not exist. Let's examine each of these situations more carefully. Our first example involves a function whose behavior changes at x equal to 1. To the right of 1, the numerator and denominator have the same sign. Look at g of x. Therefore, the function value is 1. To the left of 1, the numerator and denominator have opposite signs. Therefore, the function value is -1. This creates the jump shown on the graph. As x approaches 1 from the left, the function approaches -1. As x approaches 1 from the right, it approaches +1. The 2 sides are separated by a jump of 2 units. No matter how closely we zoom in around 1, that jump does not shrink. Because the function approaches 2 different numbers from the 2 sides, the two-sided limit does not exist. The second type of failure is unbounded behavior. Consider the function shown on the slide as x approaches 3. Because the denominator is squared, look at h of x, it remains positive on both sides of 3. As x gets closer to 3, the denominator becomes an extremely small positive number. Dividing 1 by an increasingly small positive number produces increasingly large outputs. Therefore, the function rises without bound from both sides. To make the idea concrete, choose any large target, say 10,000. If x is within 100th of 3, while not equal to 3, the function value will already be greater than 10,000. If we choose an even larger target, we can move x even closer to 3 and push the function beyond the target as well. The function never settles near a finite real number. Therefore, the limit does not exist as a finite real number. We often write the function approaches positive infinity to describe this behavior. However, positive infinity is not a number that the function reaches. It describes growth without bound. Our third type of failure is oscillating behavior. Consider the cosine function shown on the slide as x approaches 0. As x gets closer to 0, the magnitude of the expression inside the cosine grows without bound. As a result, the function passes through complete cycles faster and faster. The outputs continue moving between -1 and +1. No matter how small an interval we choose around 0, the function still reaches values at both extremes. In fact, infinitely many oscillations occur within every interval containing 0. Because the function never settles near one number, the limit does not exist. This example also demonstrates an important technology warning. A graphing program has limited screen resolution. It may not display all the increasingly rapid oscillations accurately. Graphs are useful, but they must be interpreted carefully. Let's do a quick check. For each graph, decide whether the limit exists as x approaches 2. Pause the video before looking at the answers at the bottom of the slide. For graph A, the limit does not exist. The left side approaches the height of the open circle, while the right side approaches the height of the solid circle. Because the two sides disagree, there is no two-sided limit. For graph B, the limit does exist, and it is 4. The graph approaches 4 from both directions. The hole at x equal to 2 has no effect on the limit. For graph C, no finite real limit exists. As x approaches 2 from either side, the function values increase without bound. These three graphs reinforce the distinction between a hole, a jump, and unbounded behavior. Let's bring the main ideas together. There are three complementary ways to work with limits. Numerically, we can build a table using x values that approach the point from both sides. Graphically, we can examine where the graph is headed near the point. And analytically, we can use algebra to simplify the function and find the exact limit. Tables and graphs help us estimate limits. Algebra allows us to confirm exact limits. More importantly, remember that a limit describes the behavior of a function near a point. It does not depend on whether the function is defined at the point or what the value has been assigned there. In the next lesson, we will study the limit laws. These laws will allow us to evaluate many limits efficiently, often through direct substitution or algebraic simplification. This concludes our introduction to finding limits graphically and numerically. Thank you for watching. In the next lesson, we will begin working with the limit laws and use algebra to evaluate limits more efficiently. I'll see you in the next lesson.